Good morning. My name is Dr. Mehboob Rana. I am the author of this presentation. This presentation deals with corrosion and corrosion control in reinforced concrete structures. Introduction to this presentation. Reinforced concrete structures are built with concrete reinforced metallic, non-metallic and composite component, vary in size and shape, low level to sky risers, water pipes, sewers, dams, bridges, dikes, pavements, and undergo chemical, electrochemical, mechanical, and physical corrosions. Global cost of corrosion. Corrosion has a very huge cost, right? As estimated, the US dollar 2.5 trillion, almost about 3.4% GDP per annum. 30% corrosion 30% cost component is due to concrete damages. US dollar 375 to US dollar 75 billion, almost 15%, 35% of global corrosion cost can be saved by applying available corrosion control know-how. What is corrosion? In fact, corrosion has been defined in many ways. Almost there are 13 definitions given by different authors. I have just taken two for your information. Corrosion is the deterioration of a material, usually metal, that results from a chemical or electrochemical reaction with its environment. This definition is given by the NACE. Second definition, which is practical as well from a engineering point of view, is given by the Fontana and Green. Corrosion is the deterioration of material because of reaction with its environment. From this, you can understand that corrosion is not that simple as it spells out. These two are the actual examples of the corrosion of the reinforced concrete structures. That is, this is a deterioration of the concrete. You can see that these boards, which are steel boards, are crowded, and the upper layer of concrete has spared off, and this shows the actual erosion of the concrete sewers, right? So these two are the typical examples of the corrosion as encountered by the reinforced concrete structures. The chemical corrosion, this slide shows you that how the chemical corrosion of concrete occurs. The chemical corrosion concrete is the carbon dioxide from the atmosphere, right, normally reacts with the water in the pores of the concrete, turning into carbonic acid. Carbonic acid reacts with the alkali, which is calcium hydroxide or sodium hydroxide in the concrete pores, and turn this calcium hydroxide to calcium carbonate. In addition to the mechanical pressure coming from calcium carbonate, the pH of the concrete pores drop to 8.5 from 13, right, which starts the corrosion of the steel in the concrete structures. And this little photograph shows that how the carbon dioxide once entered into the concrete structures, right, it forms actually a pit type of a corrosion, and the cracks appear in there. Once these cracks start appearing, there more CO2, more atmospheric water, and other corrodants like oxygens start moving into the concrete structure. This slide shows the chemical mechanical corrosion of concrete. The calcium sulfate in the concrete, it can react with tricalcium aluminate, forming attringite. Attringite is a complex compound of the concrete mixture. It has a volume which is about 227 to 700 times larger than the concrete. So when this actually compound, right, with the expansive volume puts a pressure on the adjacent concrete, it tears off any of the concrete wall in there. no matter how strong that may be. Other possibility of this chemical reaction, which is the calcium hydroxides of the concrete reacts with this silicatic acid, which comes from different sources, forming a calcium hydrosilicate to water. And then calcium hydroxide also reacts with silica, which is amorphous in nature, forming a gel. Now the gel in there, it starts absorbing more water, and it keeps on expanding and putting a mechanical pressure on the adjacent concrete, and the concrete disintegrate, developing cracks. The next slide shows the electrochemical and mechanical corrosion of the reinforced concrete. The oxygen, which is the actual main corrodant of the corrosion of the steel, which reacts with the iron of the embedded steel and the water in the pores in there and oxygen coming from the atmosphere, turning the iron into the iron hydroxide, which later takes some more oxygen and more water, right, and turn into the rust. And rust actually has a value which is 6 times of the iron, which in fact again puts the pressure on the concrete and dislodge the concrete from its integrity. The second reaction which is possible for the corrosion of the reinforcement is the chlorides and the wet chlorides and wet carbon dioxide. The iron of the reinforcement reacts with the chlorides coming from the atmosphere or from the actual mix in the water mix in the concrete or any other source reacts with the iron in there forming the iron chloride and plus water, which ultimately goes into the physical corrosion of reinforced concrete. Concrete thermal expansion, right? Water thermal expansion, water wind erosion, water wind storms, all these things are the causing the actual the deterioration of the concrete. The thermal expansion coming mainly from the high temperature, which can expand the iron in there, and the concrete due to the low temperature and high temperature cycles, and the water from the channels or the wind erosion. Wind erosion comes from the wind which contain the sand in there, and this continues right on the erosion of the concrete or the water and wind storms, which can also dislodge the buildings and can also cause a high degree of erosion and corrosion in there. Then the fatigue vibration coming from the natural right events like earthquakes, like tremors, like next door right building works or heavy machinery in the industry, which can cause the vibration of the buildings and cause the actual failure of the concrete by a fatigue and wear and tear, which is very normal in the concrete coming from the atmospheric attack. The reinforcement in there can also undergo thermal expansion because temperature, loss of fatigue and vibrations coming from the same source. And if the load is increased in there for one reason or the other, can deform the actual reinforcement in there, and those reinforcement can lose their strength and can cause the actual deterioration of the concrete. And then the tension coming from the tremors or the natural resources or the natural events causing the actual longitudinal tension on the reinforcement in there and making them to develop cracks or develop a deformation, or the compression tension coming from the compressive side of the tremors or horizontal compression, and that further decreases the strength of this reinforcement. Corrosion control method for reinforced concrete. There are so many corrosion control methods, only few are given in there. like the design. You can control the corrosion by design, material selection, quality, additives. Controlling corrosion of the reinforced. Can I did? Acha. Controlling corrosion of the reinforced concrete by design. The concrete must be corrosion resistant. Usually, the Portland cement is not a corrosion resistant. It can develop a corrosion, so it has to be mixed with other additives or another type of cement called polymer cement, which can increase the resistance of the concrete to the corrosion. And then strength is another factor which takes part in there, which needs to be by stronger the concrete, less vulnerable to the deterioration. Same way to a thickness, as you increase thickness, strength of the concrete increases, and that is how you can prevent concrete deterioration. And the overlay, which is normally put after structure is completed, and this overlay right of a different material, not of same material as the Portland cement, and it causes the actual. It prevents the corrodants entering into the concrete. Then giant space is another issue where the actual during thermal expansions, right, the concrete expands, and in order to prevent the concrete expansion, we put the giants in there, which can absorb the concrete expansion force. The curing setting time, another factor which controls the actual corrosion resistance and strength of the concrete. The curing time can vary from 6 to 24 hours, which is normal curing time, but the setting time can extend to 28 hours. And after 28 hours, the concrete takes full strength. Then the compaction takes a great role in there that compacted the concrete stronger than the concrete, and when doing compaction processes, the wires and airs and the pores, right, that can be removed from there, and the concrete becomes more compact and stronger. Other temperature, obviously, if the temperature has to be kept right where the concrete can normally cure, and also the applicant temperature needs to be less than 70 degrees centigrade. At 70 degrees, other reactions can also take part, which I'll explain later. For the reinforcement design, you need a corrosion resistant materials, right, which are type not based on the steel plus additives, or maybe like other stainless steel materials mentioned in the previous slides. And the strength has to be calculated of this. The stronger the actual reinforcement material, more stronger is the structure, and less vulnerable to corrosion. Then this type of the actual reinforcement, right, like in the boards, like in players, like tapes, like mesh, right, and size and shape, all the take part in there, right, to make the concrete and reinforcement stronger. The thickness of that is also thicker, the actual reinforcement stronger it is. The number of the actual reinforcements in there, they also play the great part in controlling the strength of the corrosion of the concrete, and placing and distribution, right, is another critical factor which can enhance the strength of the concrete and its life. Anchoring of these reinforcements is also very important, so that during the application, during the life or lifetime of the building, the actual these reinforcements stay in place and they don't just dislocate. And the welding these display the actual this one the reinforcements in there, right, is very important, because the welding is not done properly. The welding can develop its own problems, right, and it can also cause the cracking of the steel at the weld point, and this tall building can become weak. Controlling corrosion of the reinforced concrete by quality, concrete type of cement, Type of cement means not only this one, the Portland cement, other type of cement like pozzolan cement, right, and additives and admixtures are put in there, right. The quality of the concrete is actually controlled depends upon the water cement ratio, aggregate cement ratio, and mixture cement ratio, and the ratio they do always vary depending upon the concrete applications and the ultimate strength or the ultimate life of the structure and the shape of the structure and location of the structure, all that comes in there to play their parts, and mixtures and cement ratio. But only important thing is that the concrete and all the admixtures, aggregates, right, cement should be free of any loose clay in there, silts in there, dust in there. And alkalinity is a very important factor in there that need to be somewhere between 12 to 13 in the concrete pores so that the concrete remain alkaline and it can become protective for the reinforcement, mainly for the carbon steel. Reinforcement, the quality of reinforcement depends on the elements in there like carbon, sulfur, manganese, silicon, right? And these are all the detrimental element in steel which can, right, make the steel develop corrosion issues. Then the perlite ferrite ratio, which is also very important in there, right, because the perlite corrodes, right, at the expense of the ferrite. So if the ferrite is in a larger amount, then the perlite will have high corrosion, but if the perlite is a larger amount, then the perlite will have a comparatively low corrosion per unit area. So the area effect plays part in there in the perlite ferrite corrosion. Anchoring, the way the actual all the embedments are held together, right, and its quality and the numbers of the anchoring links in there is very important to maintain and the quality of the reinforcements and the quality, the ultimate life of the building or the structure. Welding of these, quality of the welding, right, in of these reinforcements also controls the let quality of the overall reinforcement in there, which in fact in turn gives concrete structure longer life. The bond strength is between the actual concrete and the reinforcement in there. Stronger the bond, more compact and more durable is the building. Then the connection of those concretes in there, reinforcement in there to the different application and done later in the service life also is very important. If those connections are made weak and they are subjected to corrosion, then definitely the eventual effect of the this eventual effect to the building will be rather more, right, injurious, and the building will have a low less life. Controlling corrosion of concrete embedded steel by additives. These additives are commonly called corrosion inhibitors, and the most common of them is the actual calcium nitride, right? And it's generally added as a 1 to 2% of the cement weight. But most important thing is the ratio of the nitride to chloride. So, right? If should this rate should be nitrite should be more than the actual chlorides in there, right? And generally 1 to 2% of the cement weight, the calcium nitrite is added generally in percentage of the 1 to 2% in the cement into the cement to act as an inhibitor. Other inhibitors which are based on organics like amines, esters, water dimethylethanolamine plus surfactants and water, amino alcohol surfactants plus water, vapor phase inhibitor in which the vapor phase inhibitor is only useful when the chlorides, right, are less than 1% of the concrete. Then there are capillary migration inhibitors which can pass through the capillary of the concrete and eventually they can reach the reinforcements in there. And these are added in there as the corrosion inhibitors. Controlling reinforced concrete corrosion by surface treatment. Right, the all these concrete surfaces they always have capillaries and the pores. So all these capillaries and pores are to be sealed, right, before to to make sure that the atmospheric moisture right cannot ingress into the concrete. Also can use the hydrophobic type of coatings or the treatment, right, which can also prevent or repel the water from entering the concrete. Other is the polymers that can be applied, right, to the surface of the concrete and the cement mortar, right, or put in there as the overlay, and overlay must be at least 25 millimeter thick to act as a moisture preventer. Reinforcement is the main issue in there is the profile of the reinforcement, because if the profile or this the different type of right the shape or the materials are used in there, the formed steel, the twisted steel, the flat. That's a thermal hardening, right? So the steel is a thermal hardened weathering, which is in fact the making the steel to become develop a very thin rust layer which can behave as a cathode and can lower the rate of corrosion of the steel. And then we can always apply the inorganic coatings like phosphates, like chromates, like other other coatings, and the passivation is done either to the steel or to the actual this one, the stainless steel or the double stainless steel. And in all the cases, passivation is the formation of very thin oxide layer on the surface of this of the stainless steel. All the steel, right, which can lower the rate of corrosion of the of the reinforcement in there. Controlling reinforced concrete corrosion from humidity. Humidity plays a very great role in controlling initiating the corrosion of the concrete itself as well as the reinforcement in there. Carbonation starts or becomes significant only when the humidity is more than 25%, whether on the surface or inside the pores of the concrete, in order to prevent or to lower the further humidity further, right? Always additives are added like flash ash, silica, fume, blast furnace, slag, and keep the temperature high will also lower the humidity. For the reinforcements, steel corrosion is normally is in fact possible only when the water mix is there, but it only becomes significant when the relative humidity or the humidity is less than 60%. Control the reinforced concrete corrosion by isolating surfaces means that there's the environment and the actual material and the concrete surface. If there is a barrier between the two, so that the moisture and cannot enter the concrete surface, the concrete is protected from all sort of corrosion, where the corrosion is only possible when the water ingress the concrete. For that, we can use the metal barriers, non-metal plates are used to protect the outer surface of the concrete. Wrappers are used, sheets or laminates, right, of metal or non-metal filaments, and these are actually the barriers or the solid laminates are put in there to isolate the surface of the concrete from the from the environment, and this is not possible for the huge buildings. This may be only possible for the low level part of the structures, mainly at the ground levels, where all this type of right protections are added in there. And of course, if there is a possibility adding these protections at higher levels, it's also done in there. But the most useful and faster applications of isolating the concrete surface from the environment is the application of the emulsions or the coatings like siloxane coatings, silane coating, bitumen epoxy coatings, and bitumen epoxy coatings are generally not so beautiful. They're black in color and normally applied at the foundation level where they're not visible right to the public eyes. The other the for the reinforcements, right, apply the coatings like phosphorus coatings, nickel, chromium, zinc coatings, aluminium coatings. They're all applied by the thermal, by the chemical means or by the thermal means, right? And they form actually a thin layer of these coatings which are more corrosion resistant than the steel and can isolate the steel surface from the environment. Then, like the other organic coatings which can be used in there, which are the fuel bonded epoxy coatings, urethanes, acrylics, chlorinated rubber coatings are applied to the steel in there to prevent the steel from coming into contact with the moisture inside the concrete and remain unattacked by the corrodants of the concrete. Next slide shows that the how to control the microbe-induced corrosion in reinforced concrete sewer. The sewers are generally all affected by the microbiological corrosion, right? So other the possible ways of preventing this type of corrosion by using persistent, right, inner layer which can provide resistance to the corrosion of the the lining like HDP, high density polyethylene lining, or epoxy coatings are applied to control or prevent the as a control measures to the corrosion from the microbes. And the another thing is the residence time. Residence time is the how long that sewage stay in there or that dirty water is going to stay in there. If it stays longer in there, the more bacteria they form there. More bacteria colonize in there, and the extent of the microbial corrosion increases. And then thick layer means if you have a very thick concrete layer more than the normal, it can give a longer life, right? And can also stay stronger and prevent the the ingress of the bacteria down into the structure. Then higher water cement ratio, if you have high water cement ratio, means that the more water in the concrete and then can dilute the effect of these acid gases formed from the microbes. Then porosity, if it is low porosity, so that the cannot enter into the permeable. Low porosity and low permeability, right? So which can prevent the actual gases entering into the controlling secondary corrosion in reinforced concrete. Secondary corrosion means which is not directly coming from the chemical reaction or the electrochemical reaction. It is the temperature which can exceed 70 degrees centigrade, right? Attringite, which is in fact very complex and right and voluminous compound, if it forms in there, then definitely it's going to cause the cracking of the concrete. So the Concrete buildings are normally kept at temperature less than 70 degrees centigrade, lower the temperature. And also low water cement ratio helps in controlling secondary reactions and low aggregate and cement ratio, and adding fly ash slag, low evaporation rate and expansion joints, adding expansion joints and keeping the evaporation low or help right in controlling the secondary corrosion reinforced concrete as well as the secondary secondary corrosion of the reinforcement, right, is that if there's any galvanic couple, it's better if you are using two different types of reinforcement in there, right, which are different galvanic potentials. Then, of course, the one of them which is more active is going to get corroded at the expense of the other, so it's better to avoid any galvanic couple in there. Then, any corrosion coming from the stray current, right, without secondary form of corrosion, raise the resistance to this stray current path, right, one way or the other, either by applying the coatings or by increasing the thickness of that or by adding any other material between the source and the building or the structures, right, by increasing the resistance so the stray current cannot so easily, right, flow from the source, right, to the concrete reinforcement or in the concrete building. Then cathodic protection is normally applied in protecting the buildings or the reinforcement in there. If you have the cathodic protection in there, if it's partially used or maybe you have a broken reinforcement there which is not protected by the cathodic protection, and then that part of the reinforcement can become a stray current issue and can corrode at the point where the current is going to leave. Then it's always good to earth the building or earth the actually reinforcement is there so that any stray current which can pass through the soil and entering into the structure can, instead of damaging right the corrosion there, it can go through the earth and through the earthing system instead of it's coming into the reinforcement. Controlling physical corrosion reinforced concrete by using high compressive strength concrete compact, right, making more compact, use low water cement ratio, or keep water cement ratio low, permeability low, right, have very strong foundation, right, and the buildings are put at safe location and ensure that the foundation is properly compacted so the no soil slippage takes place. Otherwise, the entire building can collapse. The same is true with the reinforcement in there. That stronger the thicker the reinforcement, right, more stronger and long lasting are the reinforcement is there. And reinforce with the high strength, they can incorporate better reliability and the strength of that structure. They should be highly ductile. High ductile means that when you are going to bend them in, right, before they are put into the actual into the concrete bed, right. They had to be right bent and of course then during this concrete building is done, right. If there is highly ductile so that they can also absorb the shocks and instead of developing right stress cracking in there, they can sustain the extra shocks coming from the other sources, from the outer sources, and always make sure that the building it takes up the load as it is designed. If extra load is put in there or the higher load is put in there, the steel reinforcements they can bend and they can lose their strength, and they can bend and then they can deform, and they can actually put the pressure on the surrounding concrete, which will cause the building to develop corrosion or cracks. When the cracks are done in there, then the corrosion accelerates unabated. Then the fatigue resistant means because if the buildings are vibrating or put in a location where there's continuous source of vibrations, then the reinforcement must be capable of resisting those fatigues. Controlling erosion in reinforced concrete by controlling corrosion in the reinforced concrete by reversing corrosion. Actually, corrosion is a process where the right materials they move. Suppose that from right to left direction. In case of these reversing, we have to make them to move from corrosion process from left to right. Like irons are when the iron steel corrodes, right? The iron iron they move from the actual this sort of steel board or the steel reinforcement into the concrete and causing the corrosion, right? Same to the concrete. Concrete loses its stability when its temperature loses stability when its alkali when its pH drops, right? In order to keep the pH, when the pH drops, it's going to affect the stability of the reinforcement in there. And realkalization means restoring the hydroxide ions in the concrete, which is normally done by a process called realkalization, where the DC current is used, right? And the negative terminal of the DC current is connected to the the reinforcement like steel bars in there are made the cathode connected to the negative terminal of the battery, and the positive terminal of the battery goes to the anode, right? Anode is always put on the surface of on the outer surface of the concrete, where the outer surface is smeared with sodium carbonate or made it wet with the sodium carbonate solution, so the current can easily flow from the outer surface, which is the from the anode to the inside of the concrete. And because of the cathodic reaction taking place at the cathode, hydros, hydroxyl ions are produced, and so any loss in the alkalinity in there or in their loss in the pH in there is rather restored and re-established, right? So hydroxyl ions at the cathodes, they help in restoring the alkali, and the process called realkalization. And if possible, then the strength of the concrete can be restored by repairs methods, by repairing. Sec, right, the reversing the corrosion of the reinforcement like steel, the steel is connected to the steel is made the cathode connected to the anodes, like zinc and aluminium anodes. They are called sacrificial anodes. So instead of the steel being corroded, these anodes or these materials they corrode and they protect the steel from corrosion. That's what they are called a sacrificial cathode protection. That the zinc and aluminium anodes they sacrifice their own life to protect the life of the steel in there. Maybe to learn alternatively, we can use the impressional cathodic protection where the DC source is used and the negative terminal of the DC source is connected to the rebars in there, all right, and the positive goes to the inert node, which has to be part of the structure of the concrete building. And then when you energize the impressional system, the reinforcement becomes a cathode, so it stops its corrosion. And whereas the corrosion likely to take place at the inert at the anode, but since we are using inert anodes, they're like carbon, like iron silicon, right? They have very low corrosion rate, and the carbon doesn't corrode at all, right? Under anodic conditions, and so they can protect the reinforcement in the concrete by reversing the corrosion reaction. Last slide deals with the actual the detection and corrosion monitoring methods used for the reinforced concrete. Right, for the concrete message are that the normally the monitoring is done by the master contents, right? The master contents are in the control range, and then the concrete is supposed to be long lasting and less damaging, right, to the reinforcement in there. And then the wires, the pores, cracks are detected by techniques some as ultrasonic waves, radiography is used, the ground penetrating radar, or the fiber optic are used to prevent, are used to monitor or detect if there is, in fact, a concrete damaging coming up in there, like the number of wires have increased, or number of pores have increased, or the cracks formed in there. And these are techniques are quite commonly used in the industry at present. The For the reinforcement, right, generally it is a half cell and two half cell potential drop. Normally the one half cell means single cell, which is called in fact closed interval, like potential closed interval potential survey, and the other one is called the this direct current voltage gradient survey. If we done in there and plotted to form of the map, it's quite easy to find out the actual the likelihood of corrosion and the placing of the corrosion in there. Other thing is that if you want to know the at what rate the concrete embedment reinforcement is likely to corrode, then we can use a technique called LPR, alpha linear polarization resistance, which can measure the corrosion of the reinforcement, provided this instrument and the electrode used in the same material as the reinforcement, and it can give almost a right relative corrosion rate, not actually absolute, but it doesn't measure the corrosion of the actual steel in there, but it measures the corrosion of the probe in there. And the probe is having the same material as the reinforcements, indirectly giving a corrosion rate of the steel reinforcement. And then, like the concrete radiography, ground penetrating radar, ultrasonic waves, and fiber optics are being used for the same reason to find out the location of the reinforcement in there, the rewards and the structure and the profile of the reboards and any corrosion profile of the reboards if there is the end location of the reboards, right? Radiography, just like the x-rays are used in for the human skeleton or for the human internal skeleton, are used for the industry as well to find out the actual the skeleton, right? The reinforcement skeleton inside the concrete, and the ground penetrating radar is also finding out the cracks and the it works on principal electromagnetic right waves and can determine the location of the corrosion wires and the location of the corrosion and its extent. Then ultrasonic waves do the same thing as the other techniques. I determine the actual the location of the revars and the if there is any corrosion and if there is any profile change of the revars, which gives us the indirect corrosion of the extent of the corrosion of the revars. Thank you so much.